Welcome. On this video, we're going to be discussing the binomial expansion theorem. So let's get started. Before we discuss that theorem, let's take a look at this small introduction problem, which states, let's try to expand this expression and let's try to write down our answer in standard form. So to expand this expression, we can see that we have a binomial and it's raised to the third exponent. So one way that we can tackle this is just to write down that same expression 3 times. So 1, 2, and 3. And we're just going to multiply them by themselves. So let's start the distribution. So the first parenthesis, I'm just going to bring it down. I'm always going to multiply in pairs. So I'm going to take a look at the second and the third parenthesis. And by expansion, my first expression is x squared. Then it becomes xy. Then if I distribute that, that's another xy. And if I finally distribute, that becomes a y squared. Let's just simplify that. Now that becomes x squared plus 2xy plus y squared. We're not done. We still got to multiply them. So let's just distribute one more time. So if I distribute that, that becomes x cubed. And if I distribute that, that becomes 2x squared y. And if we distribute that, that becomes x y squared. So we're done with the x. Now let's distribute the y. So now it becomes y x squared. Let's just finish it up. We got 2x y squared. And finally, we end up with y to the third. Now, to write in standard form, let's see if we have any like terms. So x squared, this is the only term, so we're going to bring it down. But now notice that we have two terms with x squared y. So we're just going to add them up. So 2 plus 1, that is 3. So we have 3x squared y. And the same goes with xy squared. Notice that we have one here, xy squared, and we got 2xy squared. So if we add them up, we have 3x y squared. And lastly, we just have that y to the third. So let's just bring this down. There's nothing else that we can do to this expression. So let's just box it and call it my standard form. So this is the standard form of the distribution of x plus y all to the third exponent. And let's try to analyze how this is related to the binomial expansion theorem. So the first question that we have for this topic is, using the Pascal triangle, which we do have here on the right hand side, let's look at the third row and what do we observe? Well, recall that when it comes to Pascal triangle, we always start with row 0. So this is the zeroth row. This is the first, the second. So this is the third row in the Pascal triangle. So let me just box that. So we're going to take a look at the third row in the Pascal triangle. Now, how is this row related to the expression that we got as a conclusion on the introduction question? Well, notice one thing. The values that we do have for the Pascal triangle, so 1 is essentially this one. The next value in the Pascal triangle is actually the coefficient of the next term. The next value on the Pascal triangle, it's the coefficient of the next term. And the next value of the Pascal triangle, it's the coefficient of the next term. Notice that we do have a small positive 1 here. So the first thing that we can observe is that the values of the third row in Pascal triangle they correspond to the coefficients of the terms in the expansion. And now if we take a look at the second question, it states, what do we notice about the exponents of the terms in the expansion? But before we answer question number 2, I would like to just come back to question number 1 real quick and notice that the reason why we are looking at the third row, it's because that's the exponent that the binomial was being raised to. So notice that we had a binomial, x plus y, and it was all raised to the third. So that's the reason why we wanted to look at the third row. If we would have wanted to expand the same expression, but now to the seventh term, then we would be looking at the 7th row. So that would be 3, 4, 5, 6. So we would be looking at the 7th row. And you will see that the coefficients of that expression are going to coincide with the actual values that we do have on this 7th row. Now, coming back to question number 2, it states, what do we notice about the exponents of the terms in the expansion? So what do we mean by this? So what we have here in the red box is our expansion. And notice that we have two variables. We have x's and we have y's. Now, take a look at, let's just concentrate on the x's. Notice that the x's, the first term starts with x to the second, then it goes to x, it starts with x to the third, then x to the second, and then there's an imaginary one here. Then it goes to x to the first, and notice that it goes to x to the 0, because this is equivalent to just x to the 0. Now, when it comes to y, it does quite the opposite. It starts on the third exponent, but notice that it starts on the right-hand side, and it follows the same procedure. So it starts to the third, then the next term is going to have one less, which is to the second. And then the next term, there's a 1 here, is 1 less, which is going to be 1. And there's a little y to the 0 that is hidden here. Then it goes to an exponent of 0. So one thing to notice is that when we are expanding, when it comes to those variables, and if we read the expression from left to right, notice that as one increases, the other decreases. So in the first term, we got x to the third, y to the 0. On the next term, x is going to decrease by 1 and y is going to decrease by 1. Sorry, I don't think I said it right. So x is going to decrease by 1 and y is going to increase by 1. So from the third, we go to the second. From 0, we go to the first. And then the next term, same idea. X's are going to decrease by 1. So it goes from the second to the first. And the y's are going to increase by 1 from the first to the second. And the next term, x's, it is at 1, so it would take away 1, it becomes 0. And y, it increases by 1, it is 2, so now it becomes 3. So one thing to notice is that the exponents of the terms in the expansions, so the first term in the binomial starts at 3 and decreases by 1. And the second term in the binomial it starts at 0 and increases by 1. So what do we mean by the first term and the second term? Well, let's just go back to here. So the first term in the binomial, we go back to the introduction. Notice that this is the binomial that I'm referring to, the binomial that we expanded. So the first term is x. And notice that x, it started at the highest exponent, which it was 3, and it goes 1 less. So from 3 to 2 to 1 to 0. Now the second term in the binomial that we're expanding, it is y. So this is what I mean by the second term in the binomial. And the second term in the binomial, it started at 0 and it increases by 1. So this is pretty much the idea of the binomial expansion theorem. The binomial expansion theorem is a way that we're going to be using. Well, I shouldn't call it a way. It's actually a theorem that we're going to be applying every time that we want to expand binomials. And we have one way to expand binomials already. Either we multiply them and we distribute and we get a result. And now after today's lesson, we're just going to get a shortcut to still get the same result based on the observations that we just did. But let's actually state the binomial theorem. It says for any binomial raised to the n, this is always going to be equivalent to the first term, which in this case, the first term is x, and the second term, we're going to refer to it as y. And we're going to say, well, the first term, it's always going to start with n, and the second term is always going to be in 0, plus, notice that I'm leaving some space here, and you're going to see why. Then it's going to be the coefficient. Then now x is going to lose one value, so n minus 1, And now y is going to increase by 1, so it becomes 1. Then the next value is going to have a coefficient, and now x's are going to decrease by 1 more, so now it becomes x minus 2, and now y to the second. And now we're going to have some coefficient. X we're going to decrease by 1, y we're going to increase by 1. And now this is going to go forward until the second to last term, which now is going to be x, and now y n minus 1. And lastly, the last term is going to be some coefficient plus y to the n. Now notice that I'm leaving some space in front of the coefficients. We have already stated that those coefficients, we can get them from the from the Pascal triangle. But in our previous lesson, we have also said that these values are nothing more than combination, because the value of 1 can be seen as 3 choose 0. And the value of 3 can also be seen as 3 choose 1. This value of 3 can be seen as 3 choose 2. And this 1 can be seen as 3 choose 3. So we go back to the statement here. So now I know that the first coefficient on my first term can be seen as just n choose 0. So if we choose n choose 0, we're going to look at the nth row and the first term, which is always going to be 1. Then the term for the second, or the coefficient for the second term, well, that's going to be n choose 1. Then the coefficient of the next term is going to be n choose 2. Then the coefficient of the next term is going to be n choose 3. Then the second to last is n choose n minus 1. And lastly is going to be n choose n, which is going to be 1. So this is what we're saying here, is that the binomial expression, or the binomial theorem, it's saying, look, when it comes to the binomial, my first term, it's always going to be in decreasing order. So we always start with the highest term and we decrease by 1. The second term, which in this case is y, it always starts at 0 and we increase by 1. Now the coefficients for the binomial theorem are saying, I can just take a look at the nth row in the Pascal triangle. But let's say we don't want to look at the Pascal triangle and I just want to get just the value. But that's equivalent as just writing it as n choose 0, or n choose 1, or n choose 2. Now, this same statement can also be written as n0, xn, y0, because remember that this is just another way that we can write down choosing. So n choose 0, this is just a different notation, but I want for you to get exposed to it because sometimes it is written this way as well. Then instead of writing n choose 1, I could have just opened a parenthesis and called it n on top, 1 on the bottom. So x minus 1, y1. And instead of calling it n choose 2, I can just call it parenthesis n 2 on the bottom. X n to the second, y to the second, and so forward until we go to n, y to the n. So this is just a different way to just rewrite the binomial theorem. So everything that we have done so far is just theoretical, or at least just introduction to it. But let's actually apply it so you can actually see the benefit of knowing the binomial theorem. So let's take a look at the first expression. So let's try to expand x plus y to the fifth. So again, we got two ways to go about it. The first way is to write down x plus y 5 times and then distribute. So we can distribute whatever we get. We distribute. That's a lot of computation. Or we can use the binomial theorem. So what does the binomial theorem says? Well, the binomial theorem, it's saying, look, take a look at the exponent that you do have here. So we got x plus y all to the fifth. So we're going to look at my Pascal triangle, and I'm going to look at the fifth row. So 0, 1, 2, 3, 4, 5. So since this is the fifth row in my Pascal triangle, then I know one thing for sure. I know that the coefficients are going to be having those values. So I'm just going to write a 1, and I'm going to open 2 parentheses. In the first parenthesis, I'm going to place down the first expression in my binomial, which in this case, it is an x. And in the second parenthesis, I'm going to place down the second, which is a y. Now, we just got to take care of the exponents. Since this is to the fifth, My first term, which is an x, is going to start with an exponent of 5, and my next term is going to start with an exponent of 0. And then let's move on. That's my first term, if I were to expand that. Let's take a look at the coefficient. The coefficient is 5. I want to then my x, my y, but now the x's are going to decrease by 1, and the y's are going to increase by 1. So now this is x to the 4th and y to the 1st. So let's take a look at the next term. Well, the next value in this row, it is 10. So I'm going to place down the coefficient, and then I'm going to write down a parenthesis, 1 for x, 1 for y. X decreases by 1, so it becomes a 3. Y increases by 1, so it becomes a 2. And that's my third term. And we're just going to keep doing this. So the next term, it is 10. So we're going to place down a 10. 1 for x, 1 for y. X increases by 1, so it should be decreasing. So that should be a positive 2, not a 4. So x decreases by 1, so it's a 2. Y increases by 1, so it's a 3. Then move on to the next term. Then the next term is going to be 5, x, y. X decreases by 1, so it becomes a 1. Y increases by 1, so it becomes a 4. And lastly, the last term is 1. X decreases by 1, so it becomes a 0. Y increases by 1, so it becomes y to the 5th. And this is it. If we were to expand this whole expression, if we were to multiply the same expression 5 times, that's equivalent to this big expression right here. Let's just clean it up. So the first term is just x to the 5th. Because y to the 0 is 1, multiplied by 1 is just x to the 5th. So now my next term is going to be 5, x to the 4th, y to the 1st. Then my next term is 10, x to the 3rd, y to the 2nd. Then the next term is 10, x to the 2nd, y to the 3rd. All we're just making it look nicer. That's all. Now this is x to the 0, which is equivalent to 1. And 1 times 1 is 1. So my last term is just y to the 5th. So if we were to expand it, x plus y, and we were to multiply it 5 times by itself, you would obtain this result right here. We're not going to verify it because I'm not going to be doing this multiplication. You can verify yourself. But if you have done everything correctly, then notice that 2 things are going on. The coefficients that correspond to the row in Pascal triangle, and the x's and the y that increase by 1. So from 5 to 4 to 3 to 2 to 1 to 0. And the y's went from 0 to 1 to 2 to 3 to 4 to 5. And that's pretty much it. That's what that's what the binomial theorem states, or the binomial expansion theorem. Now, how is this different if my second term, it's a number? Can we still use the expansion binomial theorem? Yeah. First things first, what's my row? I'm looking at the 4th row. So let's go to Pascal triangle. Let's identify the 4th row. So 1, 2, 3, and this is my 4th row. My first term is an x. My second term is a 2. So we have everything that we need, because now the Pascal triangle is saying, the expansion binomial theorem is saying, take a look at the first term in the Pascal triangle, which is 1, and open up 2 parentheses. 1 for the first term and 1 for the second. And the first term, it's always going to start with the highest exponent, which is, this case is 4, and the next one with the lowest, which of course is 0. Move on to the next one. What's my next value in the Pascal triangle? It's 4. Then open 2 parentheses. 1 for x and 1 for 2. X's decrease by 1, so that's a 3. Y increases by 1, so that's a 1. Move on to the next term. The next term is 6. Open parenthesis, 1 for x and 1 for 2. From 3 we go to 2, and from 1 we go to 2. Then the next one. Then we got a 4. X and 2. X's increases by 1. X decreases by 1, so it goes from 2 to 1. The 2 increases by 1, so from 2 it goes to 3. And lastly, we go to 1, 2 parentheses, 1 for x, 1 for 2. X's decreases by 1, so it becomes a 0. Y increases by 1, so it becomes a 4. Now let's just clean this up. What's my next term? Well, on my first term, It's just going to be equivalent to x to the fourth, because 2 to the 0, this is 1. They're all multiplied, so 1 times x to the fourth, well, that's just x to the fourth. So x to the fourth. Then the next term is going to become 4, and I'm just going to write it out, times x to the third, and 2 to the second, well, that's just 2. Then my next one is 6 times x to the second, and 2 to the second, that's 4, plus 4 times x times, that's an 8, plus 1 times x to the second is 0, and 2 to the fourth, that's 16. And let's just clean this up a little bit. So definitely my first term is just x to the fourth. Now my next term, notice that they're all multiplying. So it doesn't really matter the order. I can just multiply the values. So 4 times 2, that's equivalent to just 8. So now I'm going to have 8x to the third. Plus, let's take a look at the next term. 6 times x to the second times 4. I can just multiply the values. So now that becomes 24 x to the second plus, take a look at the next term. 8 times 4, that's 32, so it becomes 32x. And lastly, the last term, 1 times 16, well, that's just 16. So if we would have gotten the expression x plus 2, and we would have multiplied by itself 4 times, it would have been equivalent to the expression that we got here. And all we did, we applied the expansion binomial theorem. So under the last example, notice it's going to be a little bit different. Because now we have the expression 2x minus 3y. The first thing to notice is that what we have done under the expansion binomial theorem, notice that it was always a plus. So if it's just a plus, then we can just apply the expansion binomial theorem as we have done so far. So is it still possible for us to use the expansion binomial theorem if there is a minus? Yes, all we have to do is just rewrite the expression. So instead of looking at it as 2x minus 3y, we can still look at it into it as 2x plus negative 3y all to the fifth. They are the same expression, but the only difference is that in order for us to use the binomial expansion theorem, it always has to be a plus. So we just got to fit that characteristic. And now that we have this, we can apply the binomial expansion theorem as we have done in the past. First things first, what's the row? Well, let me just bring this down. I can see that we want to raise this expression to the fifth. So I'm going to take a look at the fifth row in the Pascal triangle. So that's 0, 1, 2, 3, 4, 5. So I'm looking at this row right here. And now that I have that, let's just apply this expansion binomial theorem. So what's my first term in my expression? Well, my first term is 2x. And my second term is going to be negative 3y. So let's just apply the theorem now. My first value is 1, and I'm going to open two parentheses. On the first one is going to be the whole expression 2x, and the second one is going to be minus 3y. The first expression starts with the highest, so this is to the fifth, and the second expression goes with the lowest, so it is 0. So that's my first term. Let's move on to the next one. My next value is 5. Open two parentheses, 1 for 2x, 1 for negative 3y. 2x decreased by 1, so it becomes a 4. Minus 3y increases by 1, so it becomes a 1. That's my second term. Next one, 10. 2x and negative 3y. 2x decreases by 1, so it becomes a 3. Negative 3y increases by 1, so it becomes a 2. I want to continue it down here. Then the next value is 10 in Pascal triangle. Then 1 for 2x and 2 for negative 3y. 2x decreases by 1, so it becomes a 2. Negative 3y increases by 1, so it becomes a 3. Next value, 5. 1 parenthesis for 2x, 1 parenthesis for negative 3y. 2x decreases by 1, so it becomes a 1. Negative 3y increases by 1, so it's a 4. And the last value, which is a 1. 1 parenthesis for 2x, 1 parenthesis for negative 3y. 2x decreases by 1, 0. Negative 3y increases by 1, so that's to the fifth. So this is our final result. All we got to do at this point is just clean it up, because it just doesn't look nice and clean. So if we take a look at the first term, Negative 3y, this definitely becomes a 1 because it has an exponent of 0. So now it becomes 2 to the fifth, which is 32, x to the fifth. So that's my first term. Let's move on to the next one. So the first term is a 5. Now my next parenthesis, it becomes 16 x to the fourth, negative 3y. Then the next term, so it becomes 10. Then 2 to the third, that's 8 x to the third, times negative 3 to the second, that's positive 9 y to the second. Then let's move on to the next term. So that's a 10, 2 to the second, that's 4x to the second. And that's minus 27 y to the third, plus 5 2x, negative 3 to the fourth, that's equivalent to 81. So that becomes 81 y to the fourth. And lastly, this becomes 1. So now this becomes just negative 3 to the fifth, which is equivalent to negative 248. So negative 243, I'm sorry, y to the fifth. And now let's just clean this up. So it becomes 32 x to the fifth plus, and we multiply all the coefficients, 5 times 16 times negative 3. That's equivalent to negative 240 x to the fourth, and then it becomes just a y plus, on my next term, if I multiply all the coefficients, 10 times 8 times 9, that's equivalent to 720 x to the third, y to the second, plus, then take a look at the next term, 10 times 4 times negative 27, that's negative 1080, so x to the second, y to the third. We're almost done. Definitely a lot of work. So 5 times 2, that's 10, times 81, so that's definitely 810 x y to the fourth. And lastly, negative 293 y to the fifth. Sorry, this is supposed to be 2 negative 243. So this is negative 243. Let's just clean this up. It looks weird whenever we have plus or minus, so I'm going to just keep it as minus. And that's about it. Let's clean this up a little bit here, 243. So definitely the last problem was the one that took the most work. But you might be asking, well, that's a lot of work just to expand this. Isn't it just faster to just multiply this 5 times? That's up to you. I will prefer this. It will definitely go faster if you would have a calculator. But there are two things that I would like to point out in this problem. The first one is if we do have a negative, in order for us to use the binomial expansion theorem, it has to be written as a plus. That way I can identify the first and the second term. And whenever we do have constants that are raised to some exponents, we have to take that in consideration whenever we are simplifying. And with this, it concludes our lesson for the binomial expansion theorem.